reminder on first exam number 1, and it will be on next Friday next week, and it will be we will have cover chapters 2 to 4, and many of the questions will be chapter 4. And question 1 is compulsory, and you have to answer question 1 and choose 2 out of 3 questions from questions 2 to 4. Now, and so my hint or my tip is read the question before you answer. Okay, read the question before you answer. Now, and last Thursday we have discussed what have we discussed? We have discussed this. We have discussed this question 4.F2 on free body diagram. So do more exercises on free body diagrams. Okay, chapter 4 will be the main part in exam number 1. So find more questions to practice, to work on. Now, and after we deal with problems in 2D, let's go on with 3D problems. For 3D problems, we have now we go to page 44. Who hasn't got the page? Who hasn't got this the hard copy, the paper copy of page 44? Anybody? And who hasn't got the notes from page 45 to 60? Now we have because we are talking about equilibrium, so we always have the same equations. We have a summation f equal to 0 and summation m equal to 0, right? Now we have because it is in 3 dimensions, so we have 3 equations in force. And summation f is equal to 0, summation fy equal to 0, and summation fc equal to 0. But for moments, we have also 3 equations. These are summation fx equal to 0, summation my equal to 0, and summation fc equal to 0. And remember, some of us have made a mistake here. Remember, if we have let me take this example. Let me take an example here. And if we have, if the moments we calculate is in this direction, if we want to draw the vector, the moments vector of this rotation, we need to do it in follow the right hand rule here. Follow the right hand rule, and the vector moments. The moments vector is in this direction. Okay, follows the right hand rule. Okay, if your answer in the moments is rotation in this direction, then the moments you should mark the moments vector in this direction. I will talk about this when I give you the scripts for quiz 2. I will give it to you at 3 p.m. Okay, so remember, if we have rotation here, then to mark to write down the moments vector of this rotation, that the vector should be pointing at the direction of the form. Okay. Now, Remember this point. After you have written this down, please go to page 38. If you have finished writing this down, go to page 38. And in three-dimensional problems, we have because rigid bodies have supports, and we know that we need to draw reaction as supports. We need to draw reactions as supports, right? Now, but what are the typical types of supports in 3D problems? Let's take a look. Now, of course, we have, I will come back to page 44 later. I will come back to page 44, but let's go to page 38. Now, and we have, for example, we have cable, and we know that for cables, that this bar can move to the left, to the right, to the upwards or downwards, but it cannot move along the direction of the cable. So the cable would act a tension on the rigid body. So the direction of the force is in this direction. Okay. Also, this rod can rotate in this direction, and here, so we don't have moments. The key points are the important ones are 1, 2. Let me see, 1, 2, 1, 2, 4, and 1, 2, 4, and 10. The first one is the cable, because this rigid body can move to the up and down, or to the left and to the right, and it can rotate in all three directions, and in all 1, 2, and 3 directions. So, and the only direction it cannot move along is the direction of the cable. So we have a force. We have a force in the direction of the cable. Now, and number 2 is survey support. It is similar to number 1. So of course it can move, it can rotate in this direction, and it can rotate in this direction. It can rotate in this direction. That means, for example, for a pen, that it can rotate in of course it can rotate in this direction, and this can rotate in this direction. It can rotate in this direction, and it can rotate in this direction. Okay. And it can move to the, because we are saying it is move, so it can move, it can slide to the left and right, can slide to the front and back, and but it cannot go down or go up. So we have survey support, we have one force here. I think 1, 2, 4, and wait a minute. 1, 2, 4, 9, and 10. Now, and is it okay for the first 2, number 1 and number 2? Now we come to number 4. Number 4 is what we call a ball and socket joint. And you will see this term from time to time. Ball and socket joints are like this. Let me have a look. Wait a minute. I think I've shown you I've shown you some of these. Wait a minute. I think I've shown you some of this. Let me have a look. A typical ball and socket joints are those in our hip and in our shoulder. This one and this one. Okay. Usually we say this one. Okay, like this. In our body, is like this. This in our shoulder. So, like for example, like in our shoulder. Now, this kind of joints we can rotate in all three directions. We can rotate in this direction and here, and it fits in the third direction. So, but it cannot move to the my upper arm cannot go to the right or to the left or go up or down or go to the front or back. But it can rotate in all three directions, but it cannot move. It cannot translate. There's no translation in the three directions. So it means we don't have moments because it can rotate freely. It can rotate, but it cannot move. It cannot translate. So it means we have forces in three directions. Okay. This is our example number 4. And then we come to number, and then we talk about number 5, but you don't see this often. Now, and bearing is in mechanical engineering. Bearing is this one, but of course, if you go to shops, there's some shops would call. They just simply translate into they just say bearing. Okay. Now, there are all sorts of bearings. There are different kinds of bearings, and we have the simple one is journal bearing is the one that works with that means we have in journal bearings, and we have a we simply fill the gap between the rotating part and we simply fill the gap of rotating part and non-rotating parts by lubricants and lubricants. So. Okay. So you will see this verse later in the other courses. So we have the rotating parts, and you have the rotating parts, the rotating parts in the middle, and let's see this is which body we're talking about. And we have the support, which is not rotating. Any words that I haven't explained clearly? Now, For this kind of bearing, of course, it can rotate freely. It can, for example, we have a bearing that, of course, it can rotate freely here. Okay, it can rotate freely. It can rotate freely, and because the only thing between the shaft and the bearing is lubricant, which is, you can say, oil, and of course it can move direct freely along the axis. We can rotate, of course, the shaft can be rotated freely, and the shaft can move freely in this direction. Besides these two, you can see the movement in other four directions are not possible. For example, if you have a bearing here, then the shaft cannot move in this direction, right? It cannot move in this direction. It cannot move in this direction. And of course, it cannot move to the front and to the back and to the left and to the right. And it can only move up and down. So the other four directions, the other four directions of movement are not possible. So these four are not possible. It's okay. So for example, this pen is sharp, it can rotate in this direction, and it can move up and down. But it cannot move left and right, or it cannot move in this direction. These two are not possible. Okay, these two are not okay. And because this bearing has a length, so it cannot move in this direction. It cannot move in this direction either. It can go up and down, and it can rotate. So we have two directions of movement possible, but the other four are not okay. So we have therefore we have because four directions of movement are not possible. So we have four directions of support forces, and we have two directions of forces and two directions of moment support. It's okay. It's okay. Now for the next one. Now we go to number 9. For number 9, we have a hitch. For example, at doors. Oh, by the way, of course, when we write in Chinese in Taiwan, we will say in Taiwan we will write for example, is this one, but actually in English we would write it in E dot G dot. Okay. Because this is not English. This is actually Latin. Okay? So, but in English we always write it in E dot G dot. Okay. But of course, when you write in Chinese, for example, on online, that you write EX dot, but there's remember when we write in English, we need to have it in E dot G dot. Now for this kind of problem, for this for hinges, let's go back to hinges. Hinges like this one, that it can move in the, for example, this is the support and we have the rigid body here. So it can move in this direction, right? My tablet, my iPad can move in this direction, rotate in this direction. But if we fix the, if I fix the cover here, then can it move in other 5 directions? Seems not, right? So it cannot move to the left, to the right, up or down, front and back, and we cannot twist the iPad in other 2 directions. So the only direction possible, is this one. Okay. The only direction possible is this one. And therefore we have 5 forces here. We have 5 forces here. And among these 5, and this one is called, because this one is called, because it's an axis, of the hinge, and this is called axial thrust. And you will see this word in problem 4.105. Let me have a quick look. 4. No, 4.105. Maybe you will see this in 4.115. Sorry. Okay. And in the homework in the coming week, I will have one problem on 3-dimensional rigid body equilibrium. So, and it has a term called axial thrust, and it refers to this one. Okay. It's okay. Now we come to if you are okay, that let's go back to page 44. Let's go to page 24. Now we work on the sample problem 4.7. Now, a 20 kilogram leader used to reach high shelves in the storeroom is supported by 2 French wheels A and B mounted on the rail and by a French wheel C resting against a rail fixed to the wall. An 80 kilogram man stands on the ladder and leads to the right, and line vector of combined weight W of the ladder intersects the floor and determine the directions of A, B, and C. Now, and the question is quite small. So how do we break it down? First of all, what do we need to determine? Okay? We need to determine this way. We need to determine the reactions at A, B, and C. So this is the key point. You first need to know what are you working towards to. This is the first thing. Now the second thing is that we have two words: French wheels A and B and French wheel C. A wheel is I assume you know what this is now, but let me write it down. But about French and French one, we have French wheels A and B and French wheel C. Now, what is French? French is this one. The officially is Chinese is this one, but in your future courses you will know that it has another Chinese name called this one. Okay. It means this thing. If I draw it from the side, it is it's like this. This one. It's okay. Now the wheel at C is French. So can anybody tell me the difference between the French wheel and French wheel in the mechanics or in statics? So it's a French wheel that it has two sides here. It means the wheel cannot move left to the left or to the right. Okay? But for a French wheel, for a French wheel that it can move to the left and to the right. Okay? It's okay. And we assume, oh, by the way, and we assume it is these wheels can rotate, okay? And so we have the ladder is supported by wheels A, B, and C. So we know what's happening at the supports A, B, and C. Now, because we are working with equilibrium, so what do we need to do at the first step before the mathematics? We need to, because we are having equilibrium, so we have summation F equals 0, summation m equal to 0, summation m equal to 0. So what do we need to do before the mathematics? Draw the free-body diagram, okay? Now let's draw the free-body diagram. And for 3D problems, and please be careful in drawing free-body diagrams. I'm using this. I'm using the parametric one, and it's okay. Now, for the free-body diagram, please go. Take your time. Now we have an. At first, we draw the contour of the letter, and remember that is that's the direction of the x. That's the x direction. So, and keep an eye on your direction. Okay. And this is points A, points B, and points C here. Next, we want to draw it first and take your time. And after we draw the contour, what do we need to draw next? After the shape of the letter, and then what's the next thing we need to draw? Forces, okay? So what forces do we have? First of all, we have the combined weights of man and the letter. Combined means two added together. Now, and the weight W is acting on a point. Of course, this is acting downwards, and it goes down to a point D, and it goes down to a point D. Let me draw a point. Write D here. And points A, B, and D are all on the floor or on AC plane. So this is the one given in the figure. So what else do we need? We need the support forces. And what support forces? Which support forces we have? Do we have? Now we have, of course, for example, for wheel A, that wheel A is flange. So we have, of course, we have support force going up, Fy, and what else? Because it is a flange wheel. It is a flange wheel, so we have Fc. Of course. So sorry, I should write it in the. I should write it A, Y, and AC. That would be clearer. Sorry. A, Y, and AC. And the next one we will have, because the wheel at B is also flange, so we have BX and BY and BZ. And for wheel C, the wheel C is unflanked, so it has only one force. This is Z. So now, and because I've drawn, then you can add the. I think these are the forces we have, and then we add the dimensions because it is quite a lot of things here. So you can add them by yourself. Okay. Now, and you can add them. So how many unknowns do we have in this problem? What are the unknowns? What are the unknowns in this equation? AY, AZ, BY, BZ, and CZ. We have 5 unknowns. Now it seems we have 6 equations but 5 unknowns, which is not very logical. But when we have a look of the forces, then all forces are in the directions of y and z, and there are there forces in x direction. Seems not. So we don't have this we don't have summation fx equal to 0. So we have 5 equations only. So we have 5 unknowns and we have 5 equations. It's okay. Now, after we have 5 unknowns and 5 equations, then you can work them out and to determine all the unknowns. Then I've given you 3 equations, and I think you can work out from these 3, or you need all 5 of them, and this is on the textbook. It's okay.